In this video, we're going to focus on a particular type of reaction called the precipitation reaction, and how we can write those in what we call a net ionic equation. When we're looking at aqueous reactions, in other words, reactions in which all of our reactants are dissolved in water, we have to look at what might drive that reaction, at what might make it happen. Some of those things include the formation of a precipitate, which is an insoluble solid, which will be our focus today. Later on, we will also look at reactions that are driven by a gas formation, or possibly the formation of a weak electrolyte. Today, however, we are going to focus on precipitate formation in precipitation reactions. The writing of precipitation reactions is going to depend on knowing if a compound is soluble in water or not. In the case of molecular compounds composed of nonmetals, the molecule must be a polar molecule. This is something that we will discuss in much more detail in Chapter 8. For now, we are going to focus on ionic compounds. To determine if an ionic compound is soluble or not, we must reference a set of solubility rules, which are a list of rules that you will have to memorize. This is one half of our solubility chart. This chart lists all compounds that are soluble. We see here that almost all salts of sodium, potassium, ammonium, nitrate, chlorate, perchlorate, and acetate are soluble. This means that if one of these ions is present, then the compound is water soluble. In other words, a salt of sodium bromide will be soluble in water. And since it is a salt, that means it will split into its electrolytes, which we discussed earlier. Likewise, nearly all salts of chloride, bromide, and iodide are also soluble. However, we do see exceptions in the case of these halogens. Silver, mercury, and lead halides are not soluble. And so, something like NaCl will be soluble. However, PbCl2 will not. That is in our list of exceptions. We also see that most salts of fluoride are also soluble. However, this does get its own box because there are many notable exceptions. Magnesium fluoride, calcium fluoride, strontium fluoride, barium fluoride, and lead fluoride are not soluble. They will not dissolve in water. All other salts containing fluoride will. And finally, sulfate salts are also soluble in water, with the notable exceptions of calcium, strontium, barium, lead, and silver. All other ionic compounds containing sulfate are soluble. Next, we have our list of insoluble compounds. We see here that most of the salts of carbonate, phosphate, oxalate, chromate, and sulfide are not soluble. This means that something like calcium carbonate is not soluble in water. It will remain in its solid form. There are some notable exceptions here as well. If these salts have NH4+ or any of the alkali metals, the group 1 metals, they are soluble in water. And so, sodium carbonate will be soluble in water since it is one of the exceptions. Most metal hydroxides and oxides are also insoluble compounds, with notable exceptions again of our alkali metal hydroxides and also barium and strontium hydroxide, which are going to be soluble. In other words, calcium hydroxide, being a metal hydroxide that is not one of our exceptions, is insoluble and so will be a solid in water. Lithium hydroxide, however, lithium being an alkali metal and so one of our exceptions, is going to be soluble in water. When looking at precipitation reactions, they're most often going to happen in what we call an exchange reaction. In an exchange reaction, the anions that are present will trade places and combine with the other cation. In other words, in the example here, X is with A in the reactants. However, X will now be with B in the products. Likewise, Y will switch places, and instead of being with B in the reactants, it is now going to be with A in the products. Let's take a look at an example. If we have, for instance, sodium carbonate reacting together with calcium chloride, we know from our solubility chart that both of these are aqueous compounds. They are both soluble in water. And now we look at our new combination. Cl is now going to be together with Na. So we have to look at the rules that we learned in the last unit. We know that Na has a 1 plus charge, Cl has a 1 minus charge, so they will come together to form NaCl. That's one of our products. Likewise, Ca is now going to get together with the anion CO3, and we know that Ca has a 2 plus charge, CO3 has a 2 minus charge, and so our product is CaCO3. Finally, we do have to balance our equation. 2 NAs over here, only 1 over here, and so we fix that by having 2 NaCls. That gives us 2 Cls in our product side. We had 2 in our reactant side. So this is now a balanced equation. Now, however, we want to look at our solubility chart, and we can see that NaCl is going to be soluble, and so that will remain aqueous. However, calcium carbonate is insoluble, and so that will be a solid in water, and thus will form a precipitate. This precipitate formation is one of the driving forces of a reaction. It will make a reaction occur. We see some other examples here of some exchange reactions which form precipitates. If we have lead nitrate, which is soluble in water, and we have potassium iodide, which is also soluble in water, an exchange reaction will occur to form potassium nitrate, which is also soluble, but it would also form lead iodide, which is insoluble. Barium chloride, soluble in water. Sodium sulfate, soluble in water. They will react together to form barium sulfate, which is not soluble, as well as sodium chloride, which is soluble. And again, we will determine these precipitates and precipitate formation by using our solubility rules. Here are just some other examples of some precipitation reactions. Here we have the formation of lead chromate from the reaction of lead nitrate and potassium chromate. Here we have the formation of lead sulfide from the reaction of lead nitrate and ammonium sulfide. Here, iron 3 hydroxide forms from the reaction of iron 3 chloride plus sodium hydroxide. And finally, we see the formation of silver chromate from a reaction of silver nitrate and potassium chromate. We will write precipitation reactions in a couple of different ways. We have what we call the complete or molecular equation, which is an equation in which all substances are written as though they are molecular substances, even though we do know that some may actually exist as ions in solution. This will make a little bit more sense when we write this out in just a minute. We also have what we call ionic equations, which is the more realistic depiction of what is actually occurring, since ionic equations show us the ions that are actually in solution in our reaction. We also have what we call spectator ions. Spectator ions are simply ions that are in an equation, but they do not necessarily take part in any reaction. We will then also be writing net ionic equations, which is an ionic equation in which the spectator ions have been removed. A net ionic equation essentially shows us the principal players in the reaction. It shows us the ions that are actually participating in the precipitate formation. This is just a review of our solubility guidelines. It's the same solubility chart we looked at before. There are just some things to keep in mind and some general trends that we'll see as we go on. For instance, we see that silver compounds, silver nitrate is soluble because nitrates are soluble. However, silver chloride and silver hydroxide are not soluble, as they are exceptions to the rules. We see that sulfides, ammonium sulfide is soluble because it is an exception. However, cadmium sulfide, antimony sulfide, and lead sulfide are not soluble. We also have hydroxides. Hydroxides, generally speaking, are not soluble. However, exceptions are the group 1 metals and strontium and barium. So we see that sodium hydroxide is soluble. However, calcium hydroxide, iron 3 hydroxide, and nickel 2 hydroxide are not soluble. As you work more with precipitate reactions and the solubility table, you will get to learn some of these trends. Here we see an example of a net ionic equation. We have the reaction of copper 2 nitrate plus sodium hydroxide reacts to give us copper 2 hydroxide and sodium nitrate. The net ionic reaction in that equation is our copper 2 plus ion plus 2 hydroxide ions react to give us our copper 2 hydroxide precipitate. The net ionic equation shows us the, quote, real reaction that's going on. We'll take a look at how to write these over the next few slides. Here we have a molecular equation for the reaction of lead nitrate and potassium iodide. These come together in an exchange reaction in which our products are going to be potassium nitrate and lead iodide. And so this top is our molecular equation. It simply shows us everything that's going on. We have our aqueous lead nitrate and our aqueous potassium iodide. They're going to react together in solution to give us potassium nitrate, which is also aqueous, and lead iodide, which, when we consult our solubility chart, we see will come out as a precipitate. To move then to an ionic equation, we split up everything that is aqueous into its respective ions. In other words, lead nitrate consists of 1 lead 2 plus ion and 2 nitrate ions. We have 2 from our chemical formula, so now we have 2 nitrate ions. Note that our subscript here now becomes a coefficient, indicating that it's 2 entire nitrate ions. Likewise, our potassium iodide splits up into 2 potassium ions and 2 iodide ions. And in the product side, we have 2 potassium nitrates, which split into 2 potassium ions and 2 nitrate ions. All of these are still all aqueous species, as indicated in our molecular formula. Lead iodide, however, is a solid in our molecular formula. And so in our ionic equation, that does not break up into ions. And so we still show it as lead iodide solid. So in an ionic equation, we will never break up any solids, liquids, gases, or molecular species. So we see here our lead iodide again. We do not break up because it is a solid. Now, in order to go to a net ionic equation, we have to remember that spectator ions are ions which do not participate in the chemical reaction. In this case, our chemical reaction is the formation of our lead iodide. We can see that the only things that actually participate in the formation of lead iodide are our lead ion and our iodide ions. We can see that everything else, our nitrate and our potassium, that were aqueous in our reactant side, are still aqueous in their same exact form in the product side. That means that they were spectator ions that did not change, and they did not participate in the chemical reaction. And so to write out our net ionic equation, we cross them right out. We don't even consider them in our net ionic equation. And so we'll cancel out our spectator ions to then yield lead 2 plus aqueous plus 2 I minus aqueous, give us our lead iodide precipitate. And that now finally is the net ionic equation. So let's look at an example. In this first example, we're going to look at our reaction of silver nitrate plus barium chloride. And so to write out the full balanced equation, we're going to start with our reactants. We have lead nitrate and our barium chloride. And so in order to now determine our products, we have to see what the new combinations will be. We see that one of our combinations is going to be silver coming together with chlorine. In this step of determining the products, you're always looking for your new combinations of cations and anions. And so we have our silver 1 plus and our chlorine 1 minus. We know that those are going to come together to form AgCl. So that is our first product. Likewise, we also know that barium and nitrate are our other cation-anion combination. Barium with its 2 plus charge, nitrate with its 1 minus charge, will come together with a formula BaNO3 And so that is our other product. It's very important to note here that our subscripts change. We have no subscript on NO3 in our reactant side, but we do have a subscript on NO3 in our product side. Likewise, this 2 here on Cl disappears as we go from reactant to product. That's because this is a chemical reaction in which our reactants are combining in new combinations. Those new combinations will exist in completely different ratios. This is why we have to balance reactions. And so to balance this reaction, we see that we have 2 Cl's over here and 1 Cl over here. And so we can add a 2 in front of our AgCl. This now gives us 2 silvers in the product side. And so let's have 2 AgNO3s. We see that that now gives us 2 NO3s. We have 2 NO3s over here. So now we have our balanced molecular equation. We still need to add our states of matter. And so we consult our solubility chart. And what we see is that nearly all nitrates are soluble, and silver is not an exception to that. Therefore, silver nitrate is aqueous. Likewise, almost all chloride salts are aqueous. Barium is not an exception to that. And so barium chloride is aqueous. Silver chloride, on the other hand, in our product side, almost all salts of chloride are soluble, but silver is one of our exceptions. Therefore, silver chloride is not soluble, and so that will now be a solid on our product side. And for the last one, nitrates are soluble. Barium is not an exception to that, and therefore barium nitrate will remain aqueous. And now we're ready to write out our ionic equation. We see that silver nitrate is aqueous, therefore we will split that up into its respective ions, remembering our coefficient here. And so we get our 2 silver plus ions plus our 2 nitrate ions. Barium chloride is also aqueous, and so we will write that out as its respective ions. We have 1 barium 2 plus and 2 chlorides. Over on the product side of our equation, our silver chloride is a solid, and so we do not break that up. We simply write that as is in its solid form. Our barium nitrate, however, is aqueous, and so we will also break that up into its ions. Our barium 2 plus and our nitrate. And so now we want to look for things that stay the exact same on both sides of the equation. We can see that silver goes from its aqueous form to a solid form over here, and so that changes. However, we have 2 nitrates aqueous in the reactant side and 2 nitrates aqueous in the product side, and so we can cross those out when thinking about our net ionic equation. Likewise, barium stays the same on both sides of our equation. It's still aqueous, and so we cross that out when thinking about our equation. And so that leaves us with our 2 silver plus ions reacting with our 2 chloride minus ions to form 2 silver chlorides. And so now we're ready to write out our final net ionic equation. We have our 2 silver pluses reacting with our 2 chloride minuses to form 2 silver chloride in the solid form. Finally, we see here that we can reduce this down even further. We have 2 silver pluses and 2 chloride minuses, giving us 2 silver chlorides. And so we can reduce this down to just simply get rid of the 2's. For a final net ionic equation of Ag plus Cl minus, react to give us AgCl. Let's work through another example. Here, we're going to look at the reaction between ammonium carbonate and magnesium iodide. Our first step is to write out the full balanced molecular equation. So we start with our reactants, and we have to determine what our products are going to be. We can see that one of our new anion-cation combinations is going to be NH4, which is a 1 plus, and I, which is a 1 minus. And so a 1 plus and a 1 minus coming together will give us a formula of NH4I. Our other combination is going to come from magnesium and carbonate. Magnesium is a 2 plus, carbonate is a 2 minus, giving us a formula of MgCO3. And finally, we have to balance this. We have 2 NH4s on our reactant side, 1 on our product side. So we can place a 2 in front of our ammonium iodide. That now leaves us with 2 iodides on our product side, and we started with 2 on our reactant side. So we now have a balanced molecular equation. However, we still need to look at what the states of matter are going to be. Using our solubility chart, we see that almost all salts of ammonium are soluble. Carbonate is not an exception to that. Therefore, ammonium carbonate is aqueous. Likewise, almost all salts of iodide are soluble. Magnesium is not an exception to that. So magnesium iodide is aqueous. On our product side, once again, almost all salts of ammonium are soluble. We don't see iodide as an exception. And similarly, almost all salts of iodide are soluble, and ammonium is not an exception. And so we can see that ammonium iodide will remain aqueous. Magnesium carbonate, on the other hand, most salts of carbonate are insoluble. And magnesium is not an exception to that. And so magnesium carbonate will be insoluble and thus will form a solid precipitate. And so now we're ready to write our ionic equation. NH4 is aqueous, and so that will split up into its respective ions. We're going to have 2 NH4 plus ions, and we've got 1 CO3 2 minus ion. Mgi2 will also split up. We have 1 Mg2 plus, and we have 2 I minus, both aqueous. In our product side, we have 2 NH4 plus aqueous. We have 2 I minus aqueous. We also have our magnesium carbonate, which is a solid, and so that will all stay together. And so now let's look for our spectator ions. We can see that in the reactant side we have 2 NH4 plus, and in the product side we have 2 NH4 plus. And so we can cross those out. In the reactant side we also have 2 I minus and 2 I minus in the product side. So we can cross those out, leaving us then with only carbonate and magnesium in the reactant side and our solid precipitate in our product side. For a final net ionic equation of Mg2 plus aqueous plus CO3 2 minus aqueous react to give us our magnesium carbonate precipitate. Go through the process and practice these on your own. Start by writing out the full, balanced molecular formula, complete with states of matter. Then write out the ionic equations, and finally, cross out your spectator ions to write the net ionic equations. Pause the video now to work on these. Restart the video to check your answers. Answers shown will only be the net ionic equation. Here are all of the final net ionic equations. If this is not what you got, go back through your process, look at the total ionic equations, and see what you might have done wrong. For more practice on net ionic equations, check out the website.